Hi, I'm Felipe Lopes, and today I'll present to you our work entitled Design of a Low-Cost Series Elastic Actuator for Application in Robotic Manipulators. Human and robot cooperation need certain flexibility to adapt the robot to the environmental and partners' activities, and Series Elastic might be a serious candidate to solution these problems. The robot Valkyrie, a NASA's humanoid, is one of the several examples that they use the series elastic actuator in some joints. Basically, the series elastic actuator has an elastic element between the motor and the link, which provides some flexibility and bring advantages to the systems. Some advantages that we can measure are better interaction with humans, better force torque control, low-cost device, shock tolerance on the motor, and as reported by the Luca in book, it can reject the vibrations, but the drawback is the hysteresis. The hysteresis may cause inoccurrence. Previous work presents series elastic based on geometry and material. In geometry, the work of Dos Santos has a specific requirement for knee assistance, focusing rehabilitation robots, and low impedance to use in knee orthosis. In Capello, in 2019, they use a concept of multivariable series elastic. They use multiple equilibrium configurations. In Martins, they combine geometry and materials. They use polyurethane, and it's easy to manufacture, and it's simple to use Arduino microcontroller. And the Jarrett and McDade, they use a term of elastomer-based series elastic, E-series elastic. They use the series elastic to upper limb exoskeleton, and the work presents importance to hysteresis. Our work proposed a series elastic actuator that was lightweight, modular, and low cost, and with mechanical requirements. We first designed an Optimus profile in SolidWorks to allow the encoder measure in the angular displacement. The 7075 aluminum parts were coated in water jets, and we use a base to position these parts to put a liquid rubber on it and to wait for the cure. Mechanical restriction was the motor shaft with 8 millimeters, and the screw connecting the encoder to the series elastic that must be about 32 millimeters apart. To be lightweight, we use rubber that you connect the inner and the outer aluminum parts. In the work, we use the two rubbers of different stiffness. The soft one, the blue, is largely used in silicon molds. In the stiff one, the black, is commonly used in tires. On a hardness scale, it's common to have ranged for short A to short D, from softest to hardest. And in this case, our blue rubber is the short A10, and the black is the short A55 hardness range. At the end of the manufacturing, the blue is series elastic actuator weighs 25 grams, and the black one weighs 26 grams. To produce the series elastic actuator, we estimate 18 reais for aluminum parts and 1.2 reais for the rubber part, totally 19.2 reais per E-series elastic actuator. About modularity, in this video we show how we can change a series elastic actuator quickly and easily depending on our demands. Okay. The assembly of the elastic element is shown in the figure left, where one encoder measures the angular motor position and the encoder 2 is connected to the link and the series elastic to measure the link positions. To estimate the elastic contour, we performed a static test that we use lever theory. We know the weight and the distance to the center of the rotation at which the force is applied. This allows us to calculate the lever torque. On the other hand, we have the angular displacement of the motor and the angular displacement of the link to generate by the elastic torque. Therefore, we can calculate the torque and approximate the value of the K. The values calculated for the blue is 1.9 Newton meters radius, and the black is 8.5 Newton meters radius. The upper line is the loading sequence where we put the weights, and the bottom line is the unload sequence where we remove them one by one. We notice the presence of the hysteresis in the as expected from rubber. To validate, we made a link performance of force in the load cell. We can compare the measured torque with the performance torque by the link using the E-series elastic. The results are shown in the graph on the right. As you can see, the estimated elastic constant are very close to the measured value. And for conclusion, it is simple and practical to manufacture a low-cost series elastic actuator. The modular series elastic allows us multiple tests with hard or soft stiffness. The hysteresis may be a problem, so we need to compensate it. Using a static test, it's possible to quantify the hysteresis and study the Mullins and relaxation effects if you use a elastomer-based series elastic. Thank you for attention.